All right, let's start. Yeah, let's get started. So we're gonna finish up. I don't even know where we're at. So it was a busy weekend. I don't know if you knew, but there was like a conference or like a math conference here at SLU. It's like 700 people. It's like helping the do like run a session as well as like give talks and stuff like that. So I'm kind of dead right now, but we're gonna get through this. And we have a short week. We don't have class on Friday, so I'll do my best to get through Monday and Wednesday, and then we'll have a long week, and I'll be back. So this is where we were at last week. We were finishing up section 4.4. So this week, again, it's a shortened week, so we don't have a homework or a quiz due this week. But there is a homework that's due next week on Friday, and it's kind of two homeworks in one. So it's like 13 problems, I think. So you kind of want to do 7 problems this week and then 6 problems next week or something like that. And that's really all I have to say. I don't remember when the next exam is. I think it's like in 2.5 weeks or something like that. I think it's the first week of November on that Friday. It's on the syllabus if you care that much about it. So the last thing I wanted to talk about is kind of this problem at the top of page 9. There's a homework problem dedicated to this one, maybe 2 homework problems dedicated to this one. So I wanted to cover it. Plus, it's just a really useful technique if you're doing anything with congruency, either in this class or a number theory in the future, or I don't know, in programming. So this is called Fermat's Little theorem. And so I can't really go about like the proof of this statement because it relies on something called the Euler-Toshin function. And I'm not going to spend the class talking about that. But you just need to know the following formula. So it turns out that if P is a prime number and A is an integer that's not divisible by P, then if you do A to the P minus 1 power, it's going to be equivalent to 1 mod P. All right, so the two numbers to pay attention to here, there's the P minus 1, and then there's the mod P, right? So if you raise a number to the P minus 1 power mod P, it's going to end up being equal to 1 is the big idea. So this, I mean, maybe it seems a little opaque right now in terms of like, how is this going to be useful? But we'll see in the next example that it's going to be pretty effective, right? Before getting into the next example, though, it's worth noting that if you take this equation and you multiply both sides by A, you end up getting the following, which says that if you take an integer and you raise it to the Pth power, if you're doing mod P, it's just going to be equal to the base of that exponent, right? So it's almost like we don't have the power at all. It's like A is equivalent to A mod P, but we have like the power here. So it's a useful formula whenever you're working with powers, via like with modular arithmetic. So we'll go through a quick example and then we'll move on to more applications of congruency. So for the first example, so this is where you want to use Fermat's little theorem. Pretty much whenever you have some number raised to some sort of like monstrous power, right? So we have like 7 to the 222nd power mod 11. It's like, you don't want to actually calculate what 7 to the 222nd power is going to be. Maybe calculators aren't even capable. I'm sure they are. I'm sure calculators can tell you what this number is going to be, but you don't want to actually compute this. You want to use Fermat's little theorem. So how are we going to make use of Fermat's little theorem? Is we're going to make use of the fact that 11 is a prime number. So for this problem, we have that our P is equal to 11. And so what this tells us, or what Fermat's theorem tells us, is that by Fermat, we have that 7 to the 10th power. So this is really P minus 1, right? If we do 7 to the 10th power, that's really equal to P minus 1. So I'm going to write it up here. Is equivalent to 1 mod 11.
And does that say 7 to the power of 10?
Yeah, that's 7 to the power of 10. And so what this means,
not the writing above it.
This is I wrote it as P minus 1. So in this case, 11s are P. So I'm trying to make it more clear that this 10 is equal to 11 minus 1. So that way we kind of understand we're in the context of Fermat's little theorem here. And so the big idea is if we take this 7 to the 10th power and you raise it to the kth power for any integer, or we're going to be thinking about like positive integers here. So if k is any positive integer, and you raise 7 to the 10th power to the kth power, this is still going to be equivalent to 1 mod 11. And I should say for every k, that's a positive integer. So I'll write it like that. Right, so this gives us the framework in which we're going to be able to solve this problem, right? The main idea is you want to divide 222 by 10, and then you want to be able to write out 7 to the 222nd power is like 7 to the 10th power multiplied by something plus like some remainder. And then all you're going to have to care about at that point is going to be what the remainder is going to be. So instead of writing it out, or instead of saying things, let's write this out. So to utilize this fact, we're going to divide. So this is what I just said verbally. So we divide 222 by 10. And so what we end up finding is we have 222 is going to be equal to 22, or 10 times 22 plus 2. Right, so applying the division algorithm to 222. And now we want to rewrite 7 to the 222nd power. Instead of writing it as 222, we write it as 10 times 22 plus 2, right? So we can say something like, so 7 to the 222nd power, this is really equal to 7 to the 10 times 10 times 22 plus 2. This is the same thing. This is a property of exponents. If you do, this is the same thing as 7 to the 10th power times 22. And then this is multiplied by 7 squared. So because we have a plus in the power, this is the same as 7 times, or 7 to the 10 times 22nd power. And then you have like this times 7 squared here. And so now I'm going to write out maybe it's a little bit too much detail, but this is the same thing as 7 to the 10th power to the 22nd power multiplied by 7 squared. And now this is exactly the realm we want to be in, right? We said before that modulo 11, 7 to the 10th power to the kth power is equivalent to 1. So we know that this is going to be equivalent to 1, modulo 11, and that just leaves you with 7 squared afterwards. So this is equivalent to 1 times 7 squared mod 11, which is equal to 49 mod 11. And then you just need to find, maybe I shouldn't be putting it in parentheses like this, but yeah, I shouldn't be putting it in parentheses. It's kind of, there's like some nuance there. All we're doing is finding the remainder. Like this is the bolded mod, not like the unbolded mod. So it's really just asking for the remainder of 49 when you divide it by 11. And this is going to be equal to 5. Right, because 49 is equal to 4, or maybe I should write it as 11 times 4 plus 5. Right, so it's this 5, that's the remainder, that's our answer. Right, so this gives us a way of understanding at least exponents within mod P without actually having to compute what the power is going to be, right? You don't want to actually compute 7 to the 222nd power and then divide by 11 and find what the remainder is going to be. You want to use this theorem to make some reductions, and this is usually how it's going to play out. So there'll be a homework problem due on Friday of next week where you'll do something similar to this, and I'll probably ask the problem like this on the exam, because I like these problems, right? I like it when you take something that looks difficult, you apply a theorem, and it turns into something that's pretty easy to work with. It's like you either know it or you don't. Any questions about this one? Okay. Yeah, so that ends last week's notes. This week, we're mostly going to be talking about mathematical induction. There's usually at least people's like one of their least favorite subjects or topics in discrete math, probably tends to look at math in general. But I'm going to try and make it so maybe it will be a little bit more digestible. Before going on to mathematical induction though, I do want to go through some applications of congruencies just because I kind of just threw congruency at you without really saying like why people care about it or how it can be useful. When you're programming or doing computer science or something.
So we put this in the folder now?
Yeah, we're not gonna do the last problem. There's like a problem that mentions Carmichael's number. That was there if I needed to like, go more time, but we're good on time, so I'm just gonna move forward. You don't have to worry about like Carmichael numbers or anything like that. Okay, so we're in week 10 now. Time's flying by. I think there's only like 15 weeks in the semester, so we're almost at like the 2/3 place already. It's kind of nuts. And so I'm gonna look at maybe one application, maybe two. I kind of want to just get to mathematical induction, to be completely honest, but maybe I'll go through this first example. And the next example will show up on a future homework or something like that. And so one of the most important applications, I don't know if people have had that much like experience with programming or machine learning or data science, but something that's going to show up very frequently is like having the ability to generate a sequence of random numbers, like establishing some sort of seed, and then from that seed, being able to create a random sequence of numbers to experiment with. It's one of the most important ideas in computer science or techniques in computer science. So we're going to show how you can create a random sequence of numbers using modular arithmetic. So we're going to be looking at like pseudo-random numbers. The reason why it's referred to as pseudo-random is that it's going to seem like a random sequence of numbers, but they're going to be given by some sort of formula. So they seem random, but they're given by a formula. So it's like pseudo-random. And so as I said before, these randomly chosen numbers are often needed for computer simulations. And there's plenty of different methods that have been devised for generating numbers that have properties of randomly chosen numbers. Because numbers generated by, this is exactly what I just said. So because numbers generated by systematic methods are not truly random, they're called pseudo-random numbers. And so the most commonly used procedure for generating pseudo-random numbers is what's called the linear, I don't know how to pronounce this, congruential method. It's like congruency, congruential. That sounds right. So we choose 4 integers. There's the modulus m, that's this part here, the multiplier a, the increment c, so it's like what you're going to be adding by, and then there's the seed x naught. And so we're going to put some restrictions on the numbers we take into consideration. So assuming a is going to be between 2 and m, c is between 0 and m, and then our seed is going to be between 0 and m as well. So the modulus always serves as the upper bound for all these other terms that we have. And so from these 4 terms we have, we can generate a sequence of pseudo-random numbers denoted by some sequence xn, where the terms within the sequence are all, again, bounded above by the modulus m. And so we're going to be generating this sequence by successively using the recursively defined function given here, right? So we have some xn, like the nth term of the sequence. When we have the nth term of the sequence, we can define the n plus 1 term of the sequence via the following formula. And so many computer experiments, it should be an E. It doesn't matter. You know how to spell experiments. So many computer experiments require the generation of pseudo-random numbers between 0 and 1. These aren't necessarily going to be between 0 and 1, but the main point is that they're all less than m, or less than or equal to m. So if you take whatever your term is going to be, and then you divide it by m, it's going to be between 0 and 1. Right. So usually when you're working with random numbers in like some sort of program, you want to choose random numbers between 0 and 1. Like you want to normalize things. So I'm just going to go through an example of how this works with a concrete example. So here it's asking you to find the sequence of pseudo-random numbers generated by the linear congruential method, where we're going to let m be equal to 9. We're going to have multiplier a is equal to 7, and then increment c is equal to 4, and then the initial seed is going to be x naught is equal to 3. So it turns out there's going to be 9 terms in this sequence before it starts repeating itself. And so, I mean, if you want longer sequences, you're going to choose larger moduli or like a larger modulus. Instead of 9, you can do like 1,000 or 1 billion or something. But we don't have time to do a billion, so we're just going to do m is equal to 9. So we're just going to apply this formula over and over again. It's going to be a little redundant. I'm not going to go through every single one of them in class, but when I write out the solutions, I'll write out every single step. Right, so if we use this formula here, we have that we can write x1 in terms of our initial seed, x0. So this is going to be equal to a, where a is equal to 7, times x naught. So x0 is equal to 3. Plus our increment c, so c in this case is equal to 4. And then this is going to be mod m, where in this case our m is equal to 9. And so all you do now, I mean, you just multiply and add the numbers. So this is 21 plus 4. So this is just equal to 25 mod n, or mod 9, which is just going to be equal to 7, right? 25 is equal to 9 times 2 plus 7, the remainder 7. And so we started with the number 3. Now we're at the number 7. And so, I mean, the rest of the steps really aren't any different at all. The only thing that's going to change, so this is our x naught. The only thing that changes from step to step is now if we want to find x2, all the numbers stay the exact same, except what you're multiplying by 7, right? So in this case, x1 is equal to 7. So now we're going to be plugging in 7 to get x2. So this is our x1. This is going to be equal to 53 mod 9. And so this is going to be equal to 8. And then you just repeat over and over again. Maybe I'll do one more, and then I'll just show you how it concludes. Right, so the next step, you do x3. So to find x3, you're going to be plugging in what you found for x2. And that's the only difference that occurs, right? So you're still going to have like the 7, the 4, and the mod 9. So this is going to be 7 times what we had for x2, which was 8, plus 4, mod 9. So again, this is, I'm keep on labeling this, but this is equal to our x2. I don't know why I changed colors. And so this is going to be equal. So this is 56 plus 4 is equal to 60. So this is the same as 60 mod 9. And so this ends up being equal to 6, right? You do 9 times 6 is equal to 54, plus 6 is equal to 60. So you have remainder 6. Right, so we're getting these random sequences of numbers, right? We have, or maybe I should say pseudo-random, in that we started with 3. We are able to get 7, 8, 6. And so this process continues until you get to the 9th term. So eventually you get to the 9th term. This is going to be 7 multiplied by x8. So it turns out x8 ends up being equal to 5.
It's clear. How does 16, so the remainder, the result, that my, because I'm assuming that's the right, so I think I got and like feeling mentally confused modulus with divisors, you know?
Oh yeah, and yeah, this is just recording whatever the remainder is going to be when you divide. So like 25 divided by 9, you're going to end up getting a remainder 7, because you have like 9 times 2 is equal to 18, plus 7 gives you 25, so you have like a remainder 7. Yeah, and so what ends up happening, I didn't show this, but if you keep going through this, you have x8 ends up being equal to 5. So to get to the last term, you do 7 times 5 plus 4 mod 9. This ends up being equal to 39 mod 9, which is equal to 3. The reason why I'm illustrating this is now we're back to the initial seed that we had, right? After we went through the 9 terms, we're back at 3, which was really just equal to x naught, right? And so now if you continue applying this sequence or like this equation, you're just going to get the same numbers over again, right? So we ended up getting a random sequence of 8 numbers. And so if you wanted a longer sequence, again, you're going to choose a larger M. Like you can choose your M to be like 250 or 200,000 or something, and then you can generate a random sequence that's like 200,000 numbers in length instead of just like the numbers. But this is just for demonstrative purposes. Any questions about this example? Okay. Yeah, so there's another example I have on the next page where it's looking at what's called check digits. I think I'm going to skip this. I might come back to it later. I mean, it's a pretty cool application in the sense that it's making use of a number of different things that we've been focusing on, and that it's applying like modular arithmetic, but we're also looking at like summation notation and stuff like that. But I kind of want to make sure I spend enough time on mathematical induction because it's something students generally have difficulty with, and I don't want to have to like rush through it. So I'm going to skip the check digits part for now. I might go back to it later on. And so this is getting into chapter 5. Chapter 5 is pretty much all about mathematical induction, and then eventually you'll get into recursion, which is related to mathematical induction. And so mathematical induction is one of the most powerful proof techniques in mathematics. But again, students usually have difficulty with it. Usually you want to use mathematical induction when you want, like whenever you want to show that some sort of equation holds for every single positive integer or something like that. So before I go into like what is mathematical induction, it's usually used if you want to show like if n is any positive integer, like showing that an equation of this nature is going to end up showing or end up holding. So this is something we've used before, right? This is really the same thing as saying like this summation formula holds, which we've seen in the past, but if you want to prove it, you usually use induction. So whenever you're like going and you want to prove something for all integers, like you want to use induction. Yeah, what's the question?
Don't think I managed to write that down, sorry.
Oh, yeah, I mean, we'll go through this example later today. I'm just kind of saying things, I'm trying to motivate like why people care about mathematical induction at the moment. So you don't have to write it down. We'll scroll back down. Right, and so there's all kinds of like equations. You can talk about like the mathematical induction when proving divisibility, when you want to show like set equalities that are more general than just doing like one or two unions. Eventually like finding some equations which we've seen before, or showing like you have like prime factorization, right? So strong, like this induction is going to be very powerful. It's something you have to understand. There's probably going to be like one or two induction problems on the next exam. So but we'll get plenty of practice. There'll be the exam review and there'll be plenty of induction practice problems. Okay, so what is mathematical induction? Before going into it mathematically, there's kind of this illustration they have in the book. Maybe it'll help you think about it. Maybe it's just gonna, I don't know, hate it even more. I don't know. So there's like a quick metaphor where we're supposing we have an infinite ladder as shown in the picture here. And the question that mathematical induction solves is we want to ask, or we want to know whether we can reach every single step on this ladder. And so we're told two things. The first thing we know is we can reach the first rung of the ladder. So we can take this initial step. Yeah, I can't do anything about Canvas. I don't know. We can take this initial step onto the ladder. And then once we're on the ladder, if we can, the second thing we're assuming is if we can reach a particular rung of the ladder, we can reach whatever the next rung is going to be. Right? So we're told these two things, and we want to determine whether or not we can go onto every single rung of the ladder. And so, I mean, maybe you can already determine that the answer is going to be yes. So it's like, can we conclude that we can reach every single rung of the ladder? So by the first property, we know that we can reach the first rung of the ladder. And so because we can reach the first rung of the ladder by 2, we can also reach the second rung of the ladder. Applying 2 again, it means we can reach the third rung of the ladder, so on and so forth. So if we can reach the first rung via here, like the first property we assumed, we can always reach whatever the next rung is going to be. So if we can reach 1, property 2 tells us we can reach step 2. If we can reach step 2, property 2 tells us we can reach step 3, and then step 4, step 5, all the way up until like step k, where k is any positive integer. Right, so there are parallels to this that I'll make more clear later on. So if we continue in this way, We can show that we can reach the fourth, fifth, and so on. So after 100 uses of 2, we can reach the 101st rung. And then you can generalize to say we're able to reach every rung of the infinite ladder. So the answer ends up being yes. And so something we can verify using an important proof technique, or it's something we can verify using an important proof technique called mathematical induction. And so like the property, what we're really showing is that we can show that the property at the nth case is going to be true for every positive integer n, where p sub n is a statement that we can reach the nth rung of the ladder, right? So we're able to show that p sub n is true for every single positive integer n is the big idea here, as long as we made these two assumptions. So maybe this is something you can refer to later on after you have a better idea of like what the heck I'm actually talking about right now. And so now I'll more formally talk about mathematical induction in terms of math and logic. And so in general, mathematical induction can be used to prove statements that assert that p sub n is true for all positive integers n, where p sub n is some sort of propositional function. So this goes back to chapter 1, I believe. And so a proof by mathematical induction is going to have two parts. It's going to have a basis step, which is what we had here. So the basis step is like being able to assume we can reach the first rung of the ladder. It's sometimes called the base case. And then the second step, which is the step that requires more work, is called the inductive step. So we can show, like the next step is showing that for all positive integers k, if p sub k is true, then we want to be able to say that p of k plus 1 is going to be true, which corresponds to what we had in the second statement here, right? If you can reach a particular rung of the ladder, you can reach the next rung. In other words, if you know that p sub k is true, p sub k plus 1 is going to be true. So this should be very analogous to what we were just talking about with respect to the ladder. Right, so this is the principle of mathematical induction. So to prove that p sub n is true for all positive integers n, where p sub n is a propositional function, we complete two steps. We show the basis step is true. This is also called the base case. So I'm going to pretty much always call this the base case. That's how I learned it when I was a youngster. And so we verify that p sub 1 is going to be true. So you assume it's true for the smallest number, or you have to show it's true for the smallest number. This is like getting your foot on the rung. And then there's the inductive step. And so that means the next thing we want to show is that if p sub k is true, we want to show that p sub k plus 1 is going to be true. Right, so this is saying like if we can reach the kth rung of the ladder, we can reach the k plus 1 rung of the ladder. Right, so just thinking in terms of this this ladder analogy, I think is pretty helpful in understanding what's going on. And so there's a little bit more to be said before going into the next example. I've said this a number of times, but this is definitely one of those things where you can read this a billion times, but it's more useful to go through it with like 5 examples, right? You don't want to read this 1,000 times and then go enter the exam assuming you know what's going on here. Like really, it's just you want to go through examples, and if you go through enough examples, they'll become intuitive, and you won't even have to think that hard when working through induction problems. Right, and so there's some more terminology that's pretty useful. So there's this idea of the inductive hypothesis. So to complete the inductive step of a proof using the principle of mathematical induction, we assume that p sub k is true for an arbitrary positive integer k, and show that under this assumption, p sub k plus 1 must also be true. So the assumption that p sub k is true is what's called the inductive hypothesis. Right, so I'm going to be referring to the inductive hypothesis a number of times. It's the assumption you're making before going into the inductive step. And so once we complete both steps in a proof by mathematical induction, we've shown that p sub n is true for all positive integers, right? This is the same thing as saying we can go to any rung on the ladder from the ladder analogy. And that is, we have shown that for every n, p sub n is true, where the quantification is over the set of positive integers. So in the inductive step, logically what we're doing is showing that for every p sub k being true, we have that p sub k plus 1 is true. Okay, that's enough of me just like reading out what's written in front of us. Let's go through an example. And again, this is the important thing to understand, is working through examples, getting practice with examples, et cetera, et cetera. And all the examples, like the examples we'll be going through is going to go through all the different things we've learned throughout the semester. Like we're looking at sums, we'll look at divisibility, we'll look at set equalities, so on and so forth. So you kind of have to know what you did in chapters like 2, 3, and 4 when doing induction. All right, so this is the example we want to do. We've used this formula in the past, but we've never proven it, so we're going to prove it now. For this example, it wants you to show that if n is a positive integer, then if you take the sum of the first n elements, or the first n positive integers, it ends up being equal to n times n plus 1 over 2. And so because we want to show this for some general positive integer, we want to use mathematical induction, right? So this is our piece of n here, right? So this is piece of n. It's saying that this sum of the first n integers ends up being equal to this equation right here. And so we want to use mathematical induction. So we use mathematical induction. Instead of using mathematical induction or saying mathematical induction, I'm just going to say induction. I feel like that suffices. And so the first thing you want to do when doing a proof by induction is you want to start with the base case. This is usually the easiest part of the proof by induction. I mean, there's only 2 parts where you have to really do anything. This is the easier case. So you want to take the smallest possible number and show that the equation holds for that number, right? So in this case, we're considering the positive integers. The smallest positive integer is 1. So we're going to let n be equal to 1. And we want to show that this ends up holding, right? So you plug in n is equal to 1 into this equation here. So I'll draw a little arrow. And so this is going to be 1 times 1 plus 1. Let me make my 1's consistent. This is over 2. Right, so I'm just plugging in n is equal to 1 into this formula. So you get 1 times 1 plus 1 over 2. And so this is equal to 2 over 2, which is equal to 1, right? So what we've shown is that if we take n is equal to 1, so you just take the sum of the first integer, which is just going to be 1, positive integer is just going to be 1, it ends up being equal to n times n plus 1 over 2. So that means the base case is true. So we're happy about that. Any questions about like what I'm doing here? Like, why did I write out this equation? Like, why do we care about this? Any questions before we move on to this part, the next part? Okay. Yeah, so you take the smallest number, you make sure the equation holds. It's concrete, which makes it nice, but this is where things get a little bit more difficult, is when you do the inductive step. Usually before beginning the inductive step, I write out what the inductive hypothesis is going to be. Like, what are we assuming before doing the inductive step? So I'm going to write out what the inductive hypothesis is, and I feel like I should be doing a different color for each step. So this is going to be the inductive hypothesis. And so what we're doing with the inductive hypothesis is we're going to suppose that piece of k is true for all positive integers. Let's see, how do I want to do this? Actually, instead of saying piece of k, I'm like, this is a small thing. I want to be a little different with my notation. Let's say like piece of j is true for all positive integers, j between 1 and some number k. And so what I'm really saying here is we're supposing the following. So i.e., I'm trying to think like how I want to write this out. So we're assuming the following is true. So i.e., we end up having the following. So we end up having that 1 plus 2 all the way up to j. We're assuming we already know that this is going to be j times j plus 1 over 2. And so what we want to do is we want to show that if we assume this, or if we assume p sub j is true for all positive integers less than or equal to k, we want to show that the sum equation is going to hold for k plus 1 as well. Right? And so what we want to show now. So we want to show now that we have that 1 plus 2 all the way up to k plus 1 is going to be equal to the equation we care about. So it's going to be k. I should move this down. That way I can actually write it in a way that's a little bit larger. So we want to show that the sum of the first k plus 1 numbers is going to be equal to k plus 1 times k plus 1 plus 1 over 2, which is the same thing as having k plus 1 times k plus 2 over 2.
Is there an R over there?
Where?
Or an Induction book?
I don't know what the heck that is actually. Yeah, I don't know. I probably accidentally moved something somewhere. I would ignore it. I don't think. Oh, I grabbed this e. When I was moving this equation or something over, I accidentally grabbed this e and dragged it over. I think somehow. Okay, yeah. So that's the inductive hypothesis, and now we go through with the inductive step. All right. So this is the inductive step. And so we want to show that this equation ends up holding true. You want to show that the sum of the first k plus 1 numbers ends up being equal to this quotient we have on the right. And so we're going to start with the sum. So we're going to consider the sum of the first k plus 1 numbers. And we want to make use of various assumptions that we've already made, right? So from the inductive hypothesis, we know that the summation equation holds at k. So does anyone kind of see the logic or like how we're going to be going through this problem? Like how do we take this sum, make use of something that we've assumed in order to get to this equation here? Like, does anyone see what the step is going to be? Oh yeah, go on. You're not gonna necessarily like if you plug in k plus 1 into the formula. I would say like you wanna like start here, and then you want to perform some operations that will eventually get you to this formula here. Like if you plug in k plus 1 into the formula, you're just gonna end up getting what we have here. But then it's like harder to work backwards from here to get to where we're at here, is what I would say. Like there's a way. I mean, you could start here and then you can rewrite things to. It's kind of doing the same thing. But I kind of want to make use of the inductive hypothesis. Is kind of what I'm getting at, versus like what I have written here. Does anyone see? Yeah, it's the first example, so it's pretty new. So the idea is like you have to make use of the inductive hypothesis. So like via the inductive hypothesis, right? We assume that this sum holds for any positive integer up until k, and we have the sum of the first k numbers right here, right? So you can kind of rewrite this in the following way. This is really the same thing as 1 plus 2 all the way up into plus k plus 1. You don't really have to write it this way, but what I'm getting at is we already have the sum of the first k numbers here. And by the inductive hypothesis, we know that the sum of the first k numbers satisfies this equation that we have here, right? So you can rewrite the sum of the first k numbers as being equal to k times k plus 1 over 2. And then you still have the plus k plus 1 over here. So you still have like the plus k plus 1, right? So let me make it more clear. So this I'm underlining in blue. This turns into what we have here. And this is the inductive hypothesis. I won't go in that much detail in the future, but this is like we're making use of the inductive hypothesis here. to go from this step to this step.
In the,
Let me write it like this. It's gonna get in. Right, so we're making use of the inductive hypothesis to go from here to here. And now it's just a matter of taking this equation and then rewriting it. So that way it's going to turn into this k plus 1 multiplied by k plus 2. Right, so this is the same thing as having k times k plus 1 over 2. We want to add these things together so we can make a common denominator. So you can multiply this by 2 over 2 to get that this is going to be plus 2 times k plus 1 over 2. And then I'm going to move down. And so let's kind of write out what all these terms are going to be. So we'll get a k squared. So we have k times k, which is k squared. We have k times 1, which will give you a k. You have a 2k. So you have a plus 2k. And then you have plus 2. And then all of this is over 2. And so this is equal to k squared plus 3k plus 2 over 2. And then you can factor this out, right? You want to think of numbers that multiply into 2 and then add into 3. So that's going to be 2 and 1. So this is equal to k plus 1 times k plus 2 over 2, which is exactly what we wanted to show, right? We started off with the sum of the first k plus 1 numbers using the inductive hypothesis and some algebra. We were able to show that that was equal to k plus 1 times k plus 2 plus 2. All right, so if you want to be particularly concrete, what we've just shown is that this is equal to k plus 1 times k plus 1 plus 1 over 2. So that's to say the sum of the first k plus 1 numbers satisfies this equation that we have here. And so we've shown the inductive step, which then means like what we've effectively shown is we can always reach the next rung of the ladder. If you can reach the kth rung of the ladder, you can always get to the, if you can reach like the kth rung of the ladder, you can always get to the k plus 1 rung of the ladder. So then you can go to k plus 2, k plus 3 to infinity, right? So this is what an inductive proof is going to look like. Right, so I mean, maybe it looks a little alien, like a little difficult or confusing at the moment, but the more practice you get, the more clear it will become. Right. Yeah, question?
Explain the hypothesis again.
Yeah, I think the hardest thing is usually the inductive, like how to make use of the inductive hypothesis. And so the inductive hypothesis, I'm going to go back to the like ladder example, right? So the inductive hypothesis with respect to the rung, like the ladder analogy, like this is really the inductive hypothesis for the ladder analogy. So the inductive hypothesis is virtually saying that if we can reach the kth rung of the ladder, then we can reach the k plus 1 rung of the ladder. And so for our particular problem, the kth rung of the ladder was saying that this equation, like this summation equation, holds for all positive integers up until k, right? And so like if I replaced j with k or something like that, it means that the following equation holds for k. Like I was being a little more general and saying it's true for every integer less than k, but it's including k as well. So like the inductive hypothesis means we're assuming that this equation holds. And what we're doing is if we can say it's true for k, we want to determine whether or not it's true for k plus 1. And so how we made use of this in the actual proof is we had the sum of the first k plus 1 numbers. And in order to sum the first k plus 1 numbers, inside of that, you're going to have the sum of the first k numbers. So we really have the sum of the first k numbers here, and then you have like this plus k plus 1 that we can ignore for the time being. And so the inductive hypothesis is like we're assuming we can reach the kth rung of the ladder, which means that we know that the sum of the first k numbers is equal to this equation we have here, right? So we're assuming this is true. And then you do some algebraic manipulations in order to get to eventually showing it's true for k plus 1 as well. So I don't know if that helped, or does that help at all, or do you still have questions about it? Yeah, I mean, it really is just going to be getting enough practice. And I will say, like, usually the hard thing is understanding what you can assume via the inductive hypothesis, and then how it applies to the particular problem you're looking at. So you'll get more practice later. So, like, I don't expect everyone to understand exactly what's going on with the first example that we do. Yeah, so maybe we'll get started with the second example. I probably won't be able to get through it all, but kind of happy with where we're at today. So I'll say a little bit more about the next one. So for this example, we want to use mathematical induction to prove the following inequality. So this is something I said we're going to prove in the past, saying that n is strictly less than 2 to the nth power for all positive integers n. And so again, the first thing you want to do, like whenever you see like for all positive integers, let me say like 95% of the time, like you're going to want to use induction. That's kind of like the dead ringer that you want to use induction to prove the statement. Maybe there are some exceptions, but usually that's what it means. So the first thing we do always is we look at the base case, which is also called the basis step, which is where you look at the smallest example. That's when n is equal to 1. So we let n be equal to 1. And then we determine whether or not this equation is true for n is equal to 1. When n is equal to 1, this is going to be 1. And then this is going to be 2 to the first power, which is 2. So you can see it ends up holding true here. So when n is equal to 1, we have that 1. Or maybe I should write like n. So I'm like making sure my handwriting is somewhat legible. If n is equal to 1 is less than 2 to the first power, which is equal to 2. So that means the base case is satisfied, right? If you plug in n is equal to 1 into this equation, it ends up holding true, right? 1 is less than 2, so the base case is going to be true. Next, we have to do the inductive step. So we have to first write out what the inductive hypothesis is going to be. And maybe I'll write it out in a way that's a little less confusing. Maybe it's a little more confusing. I don't know. So the inductive hypothesis here is we're going to be assuming the following is true. We're going to assume we can reach the nth rung of the ladder. So we're going to assume that n is strictly less than 2n for all positive integers. Less than or equal to n. And then what we want to show, so we want to show the following. So we want to show now that n plus 1 is strictly less than 2 to the n plus 1. All right, so we're assuming n is strictly less than 2 to the nth power, and now we want to show that n plus 1 is strictly less than 2n plus 1. And I think I have enough time. It's not a very long proof, actually. It requires some cleverness. So maybe I'm going to write it out now, and then maybe I'll review it at the beginning of Friday's class. So this is the inductive step. So the big idea is this, right? We have n plus 1, and we want to somehow write that it's going to be less than 2 to the n plus 1. And you usually want to start with the inductive hypothesis, right? We already know that n is less than 2n, or 2 to the n, and we have an n here, right? So we know n plus 1 is going to be less than 2 to the n plus 1 by the inductive hypothesis. So this is the inductive hypothesis, or maybe I should write it like this. I don't really have a lot of time, so I'm going to abbreviate as IH, inductive hypothesis. And now you just need to find a way to write this as 2 to the n plus 1, right? So you can use more inequalities if you want, right? This is going to be less than 2 to the n plus 2 to the n. Really, we're using the base case. We know 1 is less than 2 to the n, which is equal to 2 times 2 to the n, which is equal to 2 to the n plus 1, right? And so if you follow this inequality, we have n plus 1 is less than 2 to the n plus 1, which is what we wanted to show, right? And so that concludes the proof that we always have that n will be less than 2 to the n for positive integers. Right, so I kind of went through that quickly, but it's 8:50 and I don't want to keep people over. I'll review this a little bit more in class on Wednesday and we'll look through more examples. Any other questions for ending? All right. All right, thank you. Things are going well. Yeah, I have I mean it's like the first day, so I had like a lot of videos, but we were like it's already like
He's doing this fine. Look at him.
yeah, I slept pretty well, I was like sleeping. I have a Kawhi digital piano.
Yeah, that's one of the better ones.
Yeah, I do kind of want to.
If you then I'd probably consider like a Roland.
Yeah, I need to determine what my budget's gonna be, but
Yeah.
yeah, it's things are going well. I was a little bit anxious to be honest, in that I had